rock then fell from Tommy's hand and produced a sound. Crack! When an object produces a sound, it vibrates the air particles around it, which will then vibrate its surrounding air particles, and so on. Sound waves usually travel through the air. Our ears then pick up these vibrations. Vibrations are sound waves with greater frequency we perceive as higher pitch. Vice versa, a lower frequency also means lower pitch. The amplitude of a sound wave decides how loudly we perceive the sound. This is the human ear, and this is what it looks like on the inside. This is the outer part of the ear called the pinna. This is the part of the ear that catches the sound waves. The sound then travels down the ear canal, where it then vibrates the eardrum. The eardrum is rigid and is sensitive to even the slightest changes in air pressure, which will move it back and forth. The compressions and rarefactions of a sound wave push the drum back and forth. Higher pitched sound waves move the drum more rapidly, and louder sound waves move it at a greater distance back and forth. The eardrum is an incredibly important part of the ear because it is the entire sensory element. After the eardrum comes the middle ear, a system of tiny bones called the ossicles, which amplify the sound received at the eardrum to be passed into the inner ear. These three bones are the tiniest bones in your body. They are called the hammer, anvil, and the stirrup. The hammer comes first. When the eardrum vibrates, it moves the hammer from side to side like a lever. The other end is connected to the anvil, which is then attached to the stirrup. The other end of the stirrup is attached to the cochlea, or the inner ear. The middle ear is required to amplify sound because the inner ear, or the cochlea, conducts sound through a fluid. Fluid has more inertia than air and thus is extremely hard to move. The small force of the eardrum cannot move this fluid. The total pressure must be amplified before reaching the inner ear. The cochlea is shaped like a snail shell and is one of the most complex parts of the ear. The stirrup is connected to the cochlea via the oval window. A piston-like action from the stirrup creates pressure waves in the entire cochlea. The cochlea is consisted of many membranes and tubes. The middle membrane, called the basilar membrane, is a rigid surface that extends the whole length of the cochlea. The stirrup's movement pushes and pulls on the part of the basilar membrane just below the window. This force causes a wave moving along the surface of this membrane. The basilar membrane is made up of 20,000 to 30,000 reed-like fibers that extend across the width of the cochlea. The fibers are short and stiff in the beginning, near the oval window, but become long and limber towards the other end of the tubes. This characteristic of the fibers give them different resonant frequencies. A specific wave frequency will resonate perfectly with the fibers at a certain point along the membrane. A resonant frequency causes the fibers to vibrate rapidly. Higher frequency waves vibrate fibers close to the oval window and decrease in frequency at the other end of the membrane. This is similar to how a tuning fork works. A structure called the organ of Corti lies on the surface of the basilar membrane and extends across the length of the cochlea. This is the structure that allows our brains to hear the sound. There are hair cells in the organ of Corti that send electrical impulses through the cochlear nerve and then to the brain. So now that you understand how the ear works, let's talk of threshold of hearing. In humans, the audible range of frequencies is usually from 20 to 20,000 hertz. However, this number varies from person to person, as you could guess. Young children can generally hear frequencies that are higher than those older than them. Humans are unable to detect sound waves with frequencies lower or higher than this range. As a result, we cannot hear infrasonic sound waves or ultrasonic sound waves. Infrasonic sound waves are too low in frequency, and ultrasonic sound waves are too high. The threshold of hearing is the limits of sound intensity we are able to perceive. It is usually expressed in decibels, from 0 decibels, the threshold of hearing, and 120 decibels, the threshold of pain. And that, ladies and gentlemen, is how little Tommy can hear the sound of the rock hitting the ground.